All right, we're starting a new unit, electromagnetic induction. Let's just go for it. So magnetic field lines point to where a compass would point and are strongest where closest together. So if I were to put a compass at any point along the magnetic field lines on here, they would always be pointing the same direction as them. Our compasses point to our North Pole, but because we've defined the part of the compass that points north as a north magnet, that means it's attracted to a south pole. So magnetic field lines should flow from north to south. So I should get some field lines that look like that, some that come out here like that, some that continue off into infinity. But you'll notice they're closest together right by the poles of the magnet. That makes sense. So permanent magnets, otherwise known as dipoles, always have a north and a south pole. Hey, look at that, 2 poles, dipoles. That's pretty neat. If I were to put 2 magnets next to each other, north, south, north, south, what's going to be cool here is we'll always point from north to south, so we'll get field lines that look like that. And it'll continue, they'll go up and over and out, and then the ones over here will continue on like this. Ones here point in. Cool, you get the idea. Now, if I were to put it north to north or south to south, they should look identical, other than the direction of arrows. So from north to south, in this case, they would get reflected back. Field lines, just like with electric field lines, they're never going to cross. We'll have lines that come in like that on both ends. Cool beans. Up here, we know that Earth is a magnet, obviously, because we use magnets to track our location on it. Just like I was saying, we have a south pole at our we have a magnetic south pole at our geographic north pole, and we have our north pole at our geographic south pole. Now, it's not very stable where it's at. It's generated by moving charges in the inside of Earth. So it moves around, and you can actually look up maps where they track where the location of the poles have been. So they're never at the same place. This one, I think, is somewhere in northern Canada right now is where our north pole is. And last thing we're going to talk about with magnets is what happens when you break a magnet. You got a north side, a south side. I break it in the middle. Oh, I got a north and a south. No, magnets just continue. So if you look closely, we have our field lines going like this. The field lines actually continue inside of a magnet. So if I were to break it, boom, the field lines are going to continue, but now they have a new place where they can jump back around to. They're going to continue in the same direction. So what does that tell us? North side, south side, north side, south side. They just turn into 2 new magnets. And that's it for our first section on electromagnetic induction.